Hi. Today we're going to look at applications of logical effort theory to circuit design. We will be solving examples. And yeah, so let's get started. On the display, you see basically an example similar to the one that we have discussed in our previous lecture, the decoder design, okay, where we have alternative designs, okay. Question is, we're going to design a 6-input AND gate, and we can choose, we have 4 topologies as shown here, and initially we're going to develop an expression for the delay for each application, okay. And we are by assuming that the electrical effort, the output capacitance divided by the input capacitance, is H. And then we will decide, okay, we will do calculations, of course, in order to decide, okay, which one is going to be the fastest for H is equal to 1, H is equal to 5, H is equal to 20. But first we will do this intuitively, okay? We will make a guess. Guesses based on the expressions that we have developed. So let's get started by developing the expressions. In the first design here, let's call this one design A, this one B, this one design C, this one design D. What do we have? We have a 6-input what will we have? We have a 6-input NAND gate and an inverter that will realize the 6-input AND operation. And in order to develop the delay expression, we need to know the G values, logical effort values of the gates along our path. Okay, we have a single path, and we have a 6-input NAND gate and an inverter on the path. So let's first write down those expressions, okay, the G values, and the logical effort for, let's say, NAND 6 is what? If you don't remember this, you can look it up in the table, or alternatively, what you can do is you can draw, you will have 6 OR gates, PMOS transistors like this, and you will have a stack of 6 NMOS transistors. And each NMOS transistor should be what? Size of 6, so that when they add up, the total resistance is R, okay? This is going to yield a resistance of R over 6. And if I have total 6 of them, R over 6 times 6 will make it R, okay? So the NMOS transistor size is 6, and the PMOS transistors, we are assuming that one is open at a time, so we can leave them as 2. So what do we have? For each input, we will have 2 plus 6, 8 units of capacitance. And that is going to yield me a logical effort value for this one, for the gate, to be 8 over 3, the capacitance of the an equivalent inverter, okay? And P NAND 6, we can also derive it from this. Okay, how many PMOS transistors will be connected to this node? There will be 6 of them, okay? So they will each introduce 2 units of capacitance, 6 times 2, and this is size 6, so 6 units of capacitance coming from this one. This will make 18 units of capacitance divided by 3 will give us basically 6 units of parasitic delay coming from for the 6-input NAND gate. Erase these parts. So yeah, for the inverter, we already know it's G is equal to 1. Let me write it down also here. G inverter 1. And we can assume that P inverter is also 1. Okay. If it's not given, you can assume it's 1. So let's look at the second implementation. In the first stage, this is a two-stage again design. And of course, yeah, let me also say that, okay, this is n is equal to 2. Okay, we have two stages. Again, for this one, n is equal to 2. Okay. The first stage is a 3-input NAND gate, and the second stage, we have a 2-input NOR gate. And for the 3-input NAND gate, we have a logical effort value, complexity measure of 5/3 compared to the inverter. And for the parasitic delay, it's going to be what? It's the number of inputs, basically. It's going to be 3, okay? For this one, it was 6. So it was 6 here. And for this one, it's practical ways. It's the number of inputs. Similar for the NOR gate we have here. So we have here a 2-input NOR gate, which we also have a logical effort value of 5/3 and a parasitic effort of basically two inputs, maybe 2. And in the third implementation, we see, again, this is a two-stage implementation. And at the first stage, we see 2-input NAND. And the second stage, we have a 3-input NOR gate. Again, implementing the same function at the end. So this is going to be G NAND 2, which is 4/3. And P NAND 2 is going to give me, is actually 2. And the logical effort value for my 3-input NOR gate is going to be, again, if you don't remember, you can look it up in the table in your slides, or you can draw a NOR schematic, okay, where we have like this, okay, 3 inputs, okay, 3 PMOS transistors stacked, okay. So each transistor has, if they were unit size, 2R resistance, okay, 2R resistance, 2R resistance. This makes up 6R resistance. And I want here basically a total resistance of R. So in order to achieve that, what do I need to do? I need to be dividing this by 6. So I will be sizing them, okay, if they were unit size, 2R resistance. If they are size 6, they will have a resistance of this value, okay? So the total resistance will be R. So this is going to be size 6, size 6, size 6. And the MOS transistors are all in parallel. We can assume that they are all size 1. So each input will have 6 plus 1, 7 units of capacitance divided by the input capacitance of our unit inverter. It's going to be 7/3. So P NOR 3, again, is going to be what? I have 6 units coming from this transistor and 3 units coming from this, 9. 9 divided by the input capacitance of the inverter is going to be 3. Or what was our shortcut? It was basically the number of inputs of our gate 3. Erase this part again. And let's look at the last implementation, okay? We have, this is a 4-stage design. In the first stage, we have 3-input NAND. So what is that? We had derived this one, 5/3, we had written it here, 5/3. And what is the parasitic of this one? It is this is a 3/3, okay? And G inverter, we already know it's 1. And the parasitic effort is going to be 1. And we have a 2-input NAND gate now. G NAND 2 is what, 4/3, and P NAND 2 is 2. And I'm not writing down the last one. It's already know what we already know. It is 1 and 1. Okay. So these are the logical effort values. If you're not convinced that these are all implementing this, the function, you can write down the expressions if you wish. Okay. What you can do is, for example, if you assume that I'm going to do it this for, let's pick up a different color. Okay, if this is A, this is B, this is C, and this is D, and this is E, and this is F, for example. Okay, what is the expression here? It is A bar. This is a NOR gate, okay, plus CD bar plus E and F, okay. Of course, this is a NOR gate, and this is the expression. When you apply this complement to the expressions inside, what do we get? We get, this will cancel out the bar here. It's going to be AB, okay. And this plus will become an AND, so, and CD, pardon me, the bar goes away. 2 bars or 2 complements will yield up the same result. And same for E and F. So what do you see here is basically A, B, C, D, E, F. They all ANDed. And this is, yeah, I mean, how you can prove that this is indeed a 6-input AND gate, okay? I'm not going to do that for the rest. You can do it as an exercise. So let's focus on the question now. And we said that, let's go with a different color now. Yeah, we are going to write down an expression first, okay? Assuming that the input to output capacitance ratio H is given as a parameter as H, okay? Let's write down the delay equation for the first implementation. What is it going to be? It has 2 stages. So the minimum delay that I can achieve is going to be D, I will say A is equal to what? It has 2 stages, and the optimum stage effort is going to be G times H. Maybe we should first write down the path efforts, okay? And then continue based on that. So let's write down, okay, what is my G? The path logical effort, okay? It's going to be the multiplication of the logical efforts of the gates along my path. So I have a 6-input NAND gate and an inverter, and the multiplication of these 2 values is going to be what? 8/3. And we see that there is no branching along the path. So what is my B? The branching effort will be 1, okay? And H is given as H. So what do we have? F is going to be what? Capital F is going to be GBH. GBH, which is going to give me 8/3 times H. And for the second implementation, what do I have? My G value is going to be what? I have 5/3 for the 3-input NAND gate and 5/3 for the 2-input NOR gate. So it's going to be 5/3 multiplied by 5/3, which is give me 25/3. Okay. And what is my branching effort? It's again 1. Okay. Don't be confused with this. There are 2 paths entering this NOR gate here. Okay. That's not a branching. Okay. I mean, that's a we are looking for output branches. Okay. At the output, we don't see any branches of this gate. We don't see any branches at the input of this. Yes, we have 2 inputs, 2 branches coming in, but that's not the branching that we're looking for. We are looking for output branching. So this is going to again be 1. And what is my F going to be? It's going to be 25, pardon, this is 9. 25/9H. And similarly, we can come up with this, the expression, I mean, for this one, this is going to be G is going to be what? Now we have a 2-input NAND gate and a 3-input NOR gate. It's going to be 4/3 times 7/3, which is going to give me 28/9. Again, B is 1. What is my F going to be? It's going to be 28/9 times H. And for this last implementation, what do we have? We have G is equal to what? The first stage is 3-input NAND gate 5/3 times 1 for the inverter times 4/3 for the 2-input NAND gate and 1 for the inverter. So at the end, it's going to be 20/9. And again, my branching effort is 1. So F is what? 20/9 times H. Okay. And these were the path logical effort values. And of course, we also have another contributor to our delay. It's the parasitic delay. So for each, let me write it down for each implementation. The capital P, the parasitic effort along the path, is simply the parasitic efforts of the individual gates along my path. So it's going to be, for this one, 6. I have 6, okay, and I have 1, okay, for the inverter. So it's going to be 6 plus 1, which is going to give me 7. And similarly for this one, you see that I'm picking up one path, okay? I mean, either this path or this path, it doesn't matter. I'm not going to sum up all the parasitic efforts that I see in my circuit. I will just pick up one path. Let's pick up this path, okay? It's going to be a NAND 3 plus a NOR 2, it's going to be 5. And similarly, if I do it for this one, it's going to be 2 plus 3 now, which is 5 again. And for this one, I have 4 stages. For the first stage, it is what? 3 units. For the second one, it's 1. For the third one, it's the NAND 2, it's 2 units. And for the last one, it's 1. So total of 7 units of parasitic delay. And if I were to write down the delay expression for each implementation, D is what? Basically, it is N times square root. For this one, it's number of stages. Let me write down first the expression for this one. Okay. It's going to be F to the power 1 over N plus P, basically. And this is going to be what? In this case, it's going to be 2 times, in parentheses, we have 8/3. I will write it down as 24/9, okay? So, because each of them have in the denominator 9, okay? So, to be consistent with these ones, so we can compare them without doing any calculations easily. This is going to be, yeah, basically 1 over 2 or square root plus 7, okay? For this one, delay is going to be what? 2 times, again, we have 2 stages, in parentheses, 25 over 9. Pardon me. This is going to be h to the power 1 over 2 or square root plus 5. And for this one, the delay is going to be 2 times 28 over 9 h to the power 1 over 2 plus 5. And for the last one, it's going to be d is equal to in this case, we have 4 stages. So n is 4. 4 times the expression was 20f, 20 over 9 h to the power 1 over 2, pardon me, 1 over 4. Okay. This is going to be 1 over 4. 4 plus the parasitic delay, it's 7. Okay. Based on these expressions, what we can do is we can compare actually. Okay. We can easily compare the 2 stages first. Okay. I mean, I cannot get the last implementation D. We see that it has the least. I mean, this expression is the least. Okay, the capital G is the least, 20 over 9. It says 28 over 9 and 25 over 9 and 8 over or 24 over 9. So this one has the least path logical effort, although it has a lot of more stages than the other ones. But the parasitic effort, you can see that it's 7, okay? And this is the same as the first implementation. Although it has 2 stages, you can see that using simpler gates, we can maintain, by increasing number of stages, we can still maintain the same parasitic delay, constant delay along our path. If you, I mean, I cannot make an immediate comparison of these 2, okay? So what I'm going to do is, basically, we can easily compare B and C, okay? We see that they have the same parasitic effort of 5, okay? And if you look at the expressions, this is 2 times 25 over 9 h, square root of this expression, and this is 28 over 9 h, okay? So everything is the same, but the expressions within the square root or the parentheses is different. And the one that has lesser, let's say, path effort, okay, this one in this case, B, will always give you a lesser delay, okay, no matter what H is. Okay, you can see that this is going to yield always a better or lesser delay than compared to C. So we can always eliminate C, okay? I mean, we don't have to look basically at C because B will always be superior to the implementation in C in terms of delay. But for the other ones, I mean, we will be basically comparing the designs A, B, and D. We already know that design C can be eliminated because B is always superior to C. So let's do the calculations based on these expressions, okay? And what we expect is as H grows, okay, the one that has the least path logical effort will will have a lesser delay as H grows. That's what we can see, okay? If this is big, you will see that this will dominate over the parasitic delay and can yield a better delay result. That's something that we can suspect from this from the expressions here. Okay, and let's see. I mean, for h is equal to 1, I would expect either A or B to be the better one, okay? But looking at the expressions here, this is 24/9, this is 25/9, I will say that this one will beat this one, because this has 2 more units of parasitic delay than the implementation in B. So for h is equal to 1, I'm expecting B to be the best. And for h is equal to 5, I don't know. They will yield, I mean, closer results, okay? I mean, yeah, again, we can say that the difference is not big, okay, big enough so that, yeah, this has lots of parasitic delay. I guess, again, this one is going to beat all of them. And for h is equal to 20, yes, h is now big, okay. This one, the last implementation, can beat the other ones in terms of delay, okay? I mean, I think, again, B and D will be the 2 candidates that will have, that might have the least delay. I'm, again, eliminating the first one because it has, again, a large parasitic delay. So let's do the calculations and see the results for and I want to write down the expressions for dA. It was what? 2 times 24/9 h. Let's put this in square root, okay? Square root plus 7 dB. This is going to be square root 25/9 plus h plus 5 and d and c. It's going to be, again, a 2-stage. This is 28/9 h plus 5, and delay of d is going to be 4 times 4 20/9 h plus 7. For h is equal to 1, okay, I will be directly writing down the results. You will see that the first one yields a delay of 10.26. The second one gives us a delay of 8.33. Okay, and the third one, yeah, is close to the second one, but it, as we said, the second one will always be superior to the third one. So that, although there is a slight difference, but yeah, you can see that it is superior. And the last implementation gives us the most delay. Okay. And as h is 5, what's going to happen is this. The first one will have a delay of 14.3. And the second one has a delay of 12.3. The third one has a delay of 13 approximately. And the last one, 14.3. As you can see that as h has grown, okay, the last one and the first one have now comparable delays. You can see as h is smaller, the first one is superior to the last implementation. Okay. So, and for h is equal to 20, we see that the results are, this is 21.7. The second one is 19.9. And the third one is 21. And the last one is 70.3. And as you can see, now this one here is the best one, and here this one is the best one, and here again this one is the best one. Okay, as expected, okay, the last implementation will give you the least delay when H is a great number, or we have a high electrical effort. And yeah, this is the end of this lecture. Hope to meet you in the next lecture.